two last basic functions in order to have our full panoply of derivative rules, and that of course is e to the x and ln of x. So here we go. Y equals e to the x. As we've done with each of these, let's start with some graph analysis. And so sketch yourself a graph of e to the x. So what do I know about e to the x? Well, I know it's got a horizontal asymptote, and that horizontal asymptote is at y equals 0. E to the x is never negative. All right, what else do we know about e to the x? Well, I know that its value increases all throughout its domain. What else do I know? Well, I can also talk about end behavior. I know that asymptotically, this thing approaches 0 with the negative values, but never gets there, and then it approaches infinity as x approaches, if we took the limit as x were to approach infinity, we would get infinity, and the limit as x approaches negative infinity, we would get 0. The other thing I know about it is at x equals 0, the value of this is 1. So let's sketch that graph with all those properties. Boom. So now let's talk about the slope of that function. I think the first thing we can see about that slope is that it is always positive. Okay. What else can I say about that slope? I can say that as x approaches negative infinity, the slope trends to 0. And then as x approaches positive infinity, the slope trends itself to infinity because the slope is always increasing. Well, that's super interesting, right? Because it kind of seems like all of these things that describe the slope also describe the value of the function. Super interesting there. But let's prove it. How do I prove it? Of course, I prove it using the definition of the derivative. So here we go. If I have y is equal to e to the x, if I want dy dx, I do the limit as delta x approaches 0 of e to the x plus delta x minus e to the x all over delta x. If I plugged in 0, I would get an indeterminate form, so let's transform the function. If I've got e to the a plus b, well, that's equal to e to the a times e to the b. So limit as delta x approaches 0 of e to the x times e to the delta x minus e to the x all over delta x. So what can I do here? Well, looks like I can pull out an e to the x. And not only can I pull it out, I can pull it through the limit operation. Why? The limit operation only acts on delta x terms, not on e to the x terms. So I've got e to the x limit as delta x approaches 0 of e to the delta x minus 1 over delta x. All right, well, I don't know that one, so it looks like I'm doing a numerical evaluation of that thing. So here we go. Negative 0.1, negative 0.05, negative 0.01, 0.01, 0.05, 0.1. Boom, right? So take a moment, plug those things into your calculator. It's a good way to know how your calculator does e to the whatever. Oh, there's mine. Okay, so negative 0.1, shift, oh, okay, shift e to the negative 0.1. Oh, I see. Hold on a second. This calculator is terrible. Okay, negative 0.1. Okay. All right, cool. Divided by negative 0.1. All right, so what am I getting here? I'm getting negative. Oh, I forgot to subtract off the 1. Sorry. I'm not used to this particular calculator with this this thing. To the negative 0.1. Okay, minus 1 divided by. Okay, there we go. I've got 0.9516. Never go into any situation like a testing situation, not having used that calculator before, you're just setting yourself up for disaster. That's why I'm always reluctant to lend people calculators on exams, because they end up with just not knowing how to use the damn thing. And that causes just as much stress as not having it. So just do yourself a favor and make sure you have your calculator with you at all points. A life skill. I mean, nowadays though, like, let's be realistic. Your phone is a good enough calculator to do most of this stuff. So what's the chances that you don't have your phone on you? I mean, let's be real. Okay. And of course, I'm just stalling for time as I'm calculating. Okay. All right. Hope your day has been delightful so far. I think we see where this is going, but completion sake is super important. And by the way, the reason why it's super important is because since we're not doing this in a rigorous fashion, we have to hold ourselves to a higher standard of evidence. All right, so clearly this is approaching 1 and that's approaching 1. So the limit as delta x approaches 0 of e to the delta x minus 1 over delta x is equal to 1. Okay. Oh, so this whole thing goes to 1. Huh. Oh, e to the x. Well, that's interesting. Look at that. The derivative of e to the x is e to the x. It is its own oh my, think about the implications of that. E is an irrational number, right? Like, it just keeps going. When you raise it to a power, the value of that power, right, tells you at that point in the domain, the value of the function is equal to the value of the slope at every point in the domain. The way that the function is changing is identical to the value of the function at that point. That's just mind-blowing. Now, if you think about it, there must be one and only one number, real number, such that it is its own derivative when raised to a power where that power is the element of the domain where we're evaluating that function. That's really what E is, right? That Euler's number is derived conceptually from wanting or knowing that there's got to be some number raised to a power whose slope is equal to its own value, right? And if you look at all the different ways that Euler derives the identity of E, this I think is the most cogent one, the one that has the most impact because it gives uniqueness to that value. So fun. Then if you think about it, well, why then is the log-based E called the natural logarithm? Well, what could be more natural than a logarithm that's based on a function whose way that it's changing is the value of the function, and that's why it's natural. All right, sorry, got a little bit waxing poetic and deep there. It's just something that I love. There we go. So here we go. Boom. First thing I know, this has a vertical asymptote at x equals 0. Okay. I know it's got an x-intercept at 1. And I know that that's what happens there. That as x approaches 0, this thing approaches negative infinity. And as the graph approaches, as x approaches infinity, y approaches infinity as well, right? So it's just the reflection of this graph about the y equals x line, of the e to the x graph about the y equals x line. So there we go. Yeah, so let's talk about the slope. So the slope does not exist for x less than 0. Okay. The slope, as x approaches 0, the slope approaches negative infinity. So as x approaches infinity, or I should say the value of this function, the value of this slope approaches negative infinity, and the value of this slope approaches infinity. Okay, cool. So those are the aspects of what we're looking for. So let's go to the definition of the derivative. So I've got dy dx is equal to the limit as delta x approaches 0 of ln of x plus delta x minus ln of delta x all over delta x. And I have massive problems with this because not only is it indeterminate form, like if I plug in, like that thing just like explodes because that's just the ln of 0 is undefined. So I have massive problems here. So let's use our log rules to rewrite this. The first thing I'm going to do here is, just because it's going to get messy with the denominators, I'm going to pull the 1 over delta x out to the front. And I know the log of two things subtracted to each other is the natural log of x plus delta x all over delta x. I'm sorry, this should not be delta x, that should be x, all over x. Great. Just to rewrite that one more time, the limit as delta x approaches 0 of 1 over delta x is the natural log of 1 plus delta x over x, just simpler. All right, so here's where this derivation differs from all the other derivations we've done. We were able in every other derivation here to pull non-delta x terms outside of the limit in order to do that evaluation. We can't here, right? It's just trapped inside the argument of the limit. So what we need to do here is just be a little bit more clever. So remember, this operation doesn't act on x, but that doesn't mean that we can't solve this for various values of x. Like for example, if we say let x equal 10, this operation literally doesn't care about what the value of x is, because it's only examining what happens to the behavior of the function as I vary values of delta x. So here's what we're going to do. We're going to do delta x and then 1 over delta x natural log of 1 plus delta x over 10, and then do our normal values here. Negative 0.5, negative 0.1, negative 0.05, 0.05, 0.1, 0.5, right? And then see what that gives us. So if I go and do the natural log of 1 plus negative 0.5 divided by 10, okay, divided by negative 0.5, I get 0.1026. Okay, I do the natural log of 1 is 1 divided by 10 Okay, I get 0.1005. If I do the natural log of 1, I don't think these are the right values I normally use, but sorry, I'm kind of like on the track. Divided by 10. Okay, we get 0.1003. Okay, if I do 1 plus 5, 10. Okay, I get 0.0998. Log of 1 plus 0.1 divided by 10 Okay, 0.0995 log of 1 plus 0.5 divided by 10 divided by 0.5. I get 0.0956. Okay, so I think you can see as delta x approaches 0, that expression approaches 0.1, and as from the left, and then from the right, it also approaches 0.1. Oh, interesting. So the limit as delta x approaches 0 of 1 over delta x ln of x plus delta x over 10 is equal to 0.1. Well, that's interesting. Let's just do one more hypothetical x value and see what we get as the limit then. So let's pick something else. Let's say as x approaches, oh, I don't know, 5, right? And so then I'm going to do delta x and 1 over delta x natural log of 1 plus delta x over 5, and do that. Now, by the way, folks, if we were together, what I would be doing is I would assign each table a different value of x, and you'd each be doing this, and we would just do comparisons rather than watching me do or listening to me do this over and over and over again. So bear with it. I think the result is worth it. So 1 minus 0.5 divided by 5. Hopefully you're following along. Okay, I get 0.2107. Okay. I get 0.2020. I figured out how to edit this a little bit. Divided by -5. Okay, I'm getting 0.2010. Okay, so now we'll go to the positives. I get 0.1990. Okay, 0.1980. Okay, and then that is 0.1906. All right, so I think clearly 0.2 is where this is approaching. So the limit as delta x approaches 0 of natural log of 1 plus delta x over 5 is equal to 0.2. So what do we notice? Hopefully what you notice is when x was 10, the value of this was 0.1. When x was 5, it's 0.2. How are these related? They're inverses. So what this actually is equal to is 1 over x. Or, very simply, the derivative of ln of x is equal to 1 over x. Now, you may say to yourself, hold on a second, that's not a proof. Yeah, I know, it's not a proof. It is not rigorous. It is a pattern. And remember, our tools are exploiting patterns. Remember, the whole point of a limit is to exploit patterns. So the pattern recognition is actually really important. In your calculus classes, you will do a much more formal version of this. Now, the second thing you might argue is, hold on a second. The 1 over x function actually has stuff in both quadrants, which is problematic because we know this thing doesn't exist. That for negative values, this doesn't exist. Right, that's the point. You would never plug negative values in this, so I don't have to worry about this portion of that hyperbola because I would never have negative values here, so I would never have the negative values here. So it doesn't matter. Right? The natural constraints in the domain of this restrict the domain of where I care about the slope of the function. Now, does this obey everything that we said it needed to? Well, we said the slope doesn't exist at 0 and at values less than 0. Yep, there's an asymptote here at x equals 0, and the argument I just made here about that if I'm not plugging into negative values here, I don't have to worry about this second half of the hyperbola. Done. As x approaches 0, the value of the slope, actually the value of the slope approaches positive infinity, right? Boom. Oh God, what the hell is I doing here? And this approach 0. You're probably just screaming at me at home about messing that up, and I apologize, right? Because look here, that's going to positive infinity in terms of value, and that's going towards 0. So there you go. So now we have our last derivative rule. We have the derivative of the natural log is equal to x. Now, by corollary, that gets us every type of log function, because I know if I have a log base a, I can turn any log base a into a log base e by doing a basis change. And that's actually how we do it when we have other logs, because oftentimes, say for example in nuclear physics, you'll have a lot of log base 2 stuff because of half-life decay. When you want to actually do the problem, you change your log base 2 into a log base e natural log, and then you can do derivatives of it, so that this formula gets us any logarithmic type function. So there you go. Those are all the derivative rules. So with all those derivative rules, believe it or not, you can pretty much do every derivative, no matter how complicated it is, as long as you're willing to work your steps and work your process.